Hey everybody, welcome to today's lecture for analysis of algorithms. Today's lecture is lecture 11 and focuses on a problem called stable marriage. So, this lecture is based on section 4.3 in the book, and you should follow along in the book because obviously there's a lot of things that I don't mention in the lecture, but which are actually quite important, and so you need to pick them up from the book. So, the first question is, what is stable marriage? What is this problem? Okay, so the stable marriage problem is actually what it sounds like, which is a little weird. It's the problem of constructing a set of marriages between men and women such that no marriage ends in divorce. Okay, so it sounds like quite an important problem. And there's a couple of things about the way we tackle this problem that makes it different from how this problem would work in the real world. Okay, so there's a number of constraints basically that we put on this marriage system, right? The first constraint is that there's an equal number of men and women. Okay, so this is not a super unrealistic a constraint, right? In the real world, there's an almost equal number of men and women. But one that's quite unrealistic is every person in this system must be married. Okay, there's no same-sex marriage, so marriage in here is between a man and a woman, and we have perfect information about people's preferences. Okay, so in the real world, we don't even have perfect information about our own preferences, which makes the whole problem kind of difficult. But when we're trying to solve this artificial problem, this computational problem, we establish these constraints, right? There's an equal number of men and women. There's no same-sex marriage. At the end of the execution of our solution, every person must be married. And we know everyone's preferences perfectly. Okay. So we're trying to marry off these men and women. Okay. And we've said that this is a stable marriage problem. So, what does that word stable mean? When we say a marriage is stable, what does that mean? Well, what it means is that the marriage won't end in divorce. Okay, so in the real world, divorce can happen because someone is unhappy. So, you're in a marriage, you don't like where you are in your life, and you get divorced. Okay. But in this fake world, under these sort of artificial conditions, we've said already in the previous slide that every person must be married, right? Now, if we say every person must be married, then how can you get divorced? Like, there's no point getting divorced if you just have to get remarried immediately. Well, the reason you get divorced is because you want to marry someone better. Okay, so if you're married and there's someone you like better than your wife, if you're a guy, would you get divorced under these circumstances? Well, not necessarily, because remember, we also need to have some idea of what is achievable for us, right? So, like, this is so silly. But basically, if you are married to somebody and you like someone else better, you're not going to leave your wife for that person unless they would also leave who they're married to come and marry you, right? So, if you leave your partner because you want to end up with a better partner, but then that person doesn't want you, then it doesn't work because you have to be married, right? So fundamentally, you'll only get divorced if there's someone who you'd run away with who'd also run away with you. Okay. Now, an important question here is why? What is happening here? Why are we even trying to solve this problem? Like, can we construct like a better society by telling people who to marry and stuff? I mean, no, we can't, right? First of all, like we said, this is a quite artificial problem. There's lots of constraints in the real world that we are not modeling. So, we can't actually use this to have people marry whoever we think they should. But actually, this is a good analogy to some resource allocation problems. So if you think of marriage as sort of allocating partners to each other, then we can sort of solve a sort of two-party resource allocation or matching problem with this analogy. Okay. As an example, where this actually comes from is the system in the US where, I mean, we have this here as well, where when medical students finish their degree, they have to go and work as an intern in a hospital for 2 years. And only after working as an intern are they actually qualified as a doctor, right? Now, this is a sort of a resource problem, and it's a a symmetrical resource problem, if I can put it that way, in that the interns need the hospitals because if they didn't have a hospital to work at, they couldn't get their degree. But at the same time, the hospitals need interns because otherwise they couldn't fix patients. So the problem that would crop up, and this was particularly severe in the US, the problem that would crop up is that an intern would apply to a number of hospitals, right? And a hospital would get tons of interns applying. And then the hospital might say, look, I don't want Pravesh because I think Richard is better. Clearly, this hospital doesn't know what he's talking about, but I don't want Pravesh, I want Richard, right? So then they turn down my job application. Crazy people, but it can happen. Richard, on the other hand, decides he doesn't want to go to that hospital. Because a better hospital comes back and tells him, hey, they want him as well. So what happens then is that the hospital that turned me down ends up with no intern because they put all their eggs in the Richard basket and then didn't get Richard. And on the other hand, like, I have no job. So the whole system kind of failed, right? So the idea is that, can we come up with a way to match these interns in hospitals in such a way that they don't get divorced? What that means is that we wouldn't match Richard to the hospital because he wanted that other hospital and that the other hospital also wanted him, right? Why this was particularly severe in the US is because there isn't a centralized health system. So, you couldn't just have the government assign you to a particular hospital because it doesn't work that way in the US. Okay, but so that's just to give you a bit of background to say that although this is a fun academic exercise, it's not only a fun academic exercise. There's also some use to it. Okay, so now if we want to actually solve this problem, we need some information. Okay, if we were talking about the hospitals and interns, what we'd need is for every intern to give us a ranked list of their hospitals and for every hospital to give us a ranked list of their interns. In our analogy, we're saying that for every man and woman, we have an ordered list representing their preferences. Okay, so let's say we have a problem of size 4, meaning there's 4 men and 4 women. Okay, so 8 people in total. Man 1 would then have a list that's an ordered list that is ordered by his preferences. So let's say he has a list that looks like this, 3, 1, 2, 0. That means his favorite woman is woman 3. Second favorite is woman 1. Third favorite is woman 2. And least favorite is woman 0. Right? So he's got a list of, which women he likes the most and the least. And we have one of these for every man and woman. Right? So every woman will do the same for the men in this world. Okay, and then we can combine this into preference arrays. Okay, so here's an example. Here's an example of a preference array for men. And this is a preference array for women. And how you read this is that this is man naught's preference array, right? This is man 1, man 2, man 3. Similarly, woman naught's preference array, woman 1's preference array. So if we look at it, man naught has the list 0, 2, 1, 3. So that means his favorite woman is woman naught. Right? We could similarly say man 2's second favorite woman is woman 3. Okay, so she's got a rank of 1. Rank 0 is the best rank. So this is the second favorite. We could say woman 1's least favorite man is man 1, right? He's the man at the bottom of her preference list or at the end of her preference list. Woman 3's third favorite man is man 2. Okay, so these were just some examples to help you understand the organization of these preference arrays. Okay, I could go on all day, but I won't. But the point here is that we know now how every man ranks every woman and how every woman ranks every man. And then what we want to produce when we solve this problem is a set of marriages. Right? So we'll have some array that says, like, for every man who they're married to. And similarly, it could be for every woman who they're married to, and it would be the same array, really, just organized differently, right? Looking at this marriage array, we're saying that man 1 is married to woman 3. Okay? So that is just some idea of how the organization of this thing works. Now, remember, the whole point was that we want to produce stable marriages, marriages that don't end in divorce. Okay, so let's look at an example. Let's look at this set of marriages. Is this set of marriages stable? Well, how do we know if it's stable? Is a marriage unstable if one partner would rather marry someone else? So let's look at an example. Maybe man one is with woman three, right? Man one is with woman three. Does that mean like man one has ended up marrying his least favorite woman? Does that mean that that marriage is unstable, right? Because he could leave to be with woman two, naught, or one, because he doesn't like woman three at all, and that's the woman that he's married to. Well, not necessarily. It's only unstable if one of these women would leave their husband for him, right? So he won't leave woman three unless a better woman would choose to be with him. Okay. So remember this idea of stability, you actually have to check both sides. You can't just say, well, the man is unhappy, therefore the marriage is unstable. It goes further than that. We can't say that the man is unhappy and the woman is unhappy, therefore the marriage is unstable. Doesn't mean that. The marriage is only unstable if the man is unhappy and someone he would leave with is also unhappy in her marriage, right? So it's not that his wife is unhappy, it's that his mistress, that's the wrong word, but the person he would leave his wife for is unhappy. It's kind of uncomfortable even saying all of this, isn't it? But anyway, let's keep on keeping on. Okay, so if we want to check the stability of the algorithm, we can use the algorithm on page 52, or the stability of the solution, sorry. We can check the algorithm on page 52. Okay, so please pause and go look at that algorithm now. Okay, so you'll notice the book uses slightly different terminology. It has boys and girls rather than men and women. That's just random. That's an arbitrary choice. Okay, so, but what the algorithm says in summary is that if I want to see if a particular marriage is unstable, let's say a marriage between a particular man and a particular woman is, I want to check whether it's stable. What I do is I check for every man that the woman likes more than her husband, does that man like her more than his wife? And if that's the case, then the marriage is unstable. So I return false, right? Because I'm checking whether it's stable. And after I've been through the whole for loop, after I've checked every man, then I can return true to say that it is stable. Meaning I've been through all possibilities that could have made this marriage unstable, and I've decided none of them is going to happen. So fundamentally, it's checking whether there's two people who would run away with each other. Okay, so if I want to check whether a whole set of marriages is unstable, like this whole marriage set, not just one partner, all I have to do is stick that logic in a for loop, right? So now I'm saying for every woman W, so for every woman that exists, then for every man that she likes more than her husband, if that man likes her more than his wife, then return false, meaning the whole set of marriages is unstable. So the set of marriages is only stable if every marriage in it is stable. So as soon as there's one unstable marriage, the whole system kind of collapses because people start running away with each other and it's just chaos. Okay, so we don't we just have a pretty simple algorithm here that checks whether a set of marriages is stable. All it was a for loop around the idea that a single person is in a stable marriage. Okay, so as an example, is this set of marriages stable? Okay, meaning would any of these end in divorce? Well, let's check. Okay, so the first marriage we have is that man naught is married to woman naught. Okay, so we said for every woman W, so let's start with woman naught. So woman naught is married to man naught, who's her least favorite man, right? So we say for every man that she likes more than her husband, which is every man, right? So let's start off with man 3. So we say man 3. Would woman naught run away with man 3? Well, only if man 3 would also run away with her, right? So let's look at man 3. Does he prefer his current wife? His current wife is woman 1 to woman naught. Yes, he does. He prefers woman 1. So he would not leave his wife for woman naught. So woman naught can't run away with man 3. Okay. Can she run away with man 1? Well, let's see. She would definitely prefer man 1 over her husband because her husband is the least favorite man. That poor woman, that sucks. But man 1 is currently married to woman 3, right? So would he run away with woman naught? Yes, he would. So we've got some instability here because woman naught would run away with man 1 and man 1 would run away with woman naught, right? Because he's currently married to his least favorite woman. So that means the set of marriages is not stable because these two would break apart. Woman naught would run away, right? So it's not stable. And we just ran through this algorithm to check, basically. So as soon as we found one unstable marriage, we stopped. Now, the next question is, how hard was it to check? And by that I mean, what is the complexity of this algorithm? So let's say that there's n women. How many times would this loop run? Well, if there's n women, it would run n times, right? So I'll say theta n, basically. Then we say for every man B that W likes more than her husband M. Okay, so let's look at a worst case analysis. This is saying we have to loop over every man that the woman likes more than her husband. Now, in the worst case, that's every other man, right? Like in this particular case where we said woman naught was married to man naught, we had to look at every other man. So that'll also take theta n, right? Strictly speaking, it'll take n minus 1. But remember, with asymptotic notation, we don't care about those constants. So n minus 1 becomes n. Okay. And then if B likes W more than his wife, well, that's the difficult part. So let's say when we were doing this, we were checking whether man 3, for instance, preferred woman naught or his current wife, woman 1. How would we do that? Okay, so I want you to pause and just think about that. What algorithm would you use? So as an example, let's say I was looking at man naught and I wanted to know whether he preferred woman 2 over woman 3 or even woman 1 over woman 3 or something like that. How would I check? Okay, pause for a second and think about it. Okay, so whether you solved it or not, it doesn't matter. How we do it is we do a linear search. Okay, so we know that this is an ordered list of preferences. So if I want to know whether man naught prefers woman 1 or woman 3, what I do is I do a linear search, and the first one I find is the one he likes more. So if I'm going down and I find woman 1 and I haven't yet found woman 3, then I know he likes woman 1 more, right? As another example, let's say for man 1, I wanted to know whether he likes woman naught or woman 3, let's say. What I do is I take a linear search and I stop when I find either woman naught or woman 3. And the one I find first is the one he likes more because I was going in order of his preference. Okay? But in the worst case, that takes theta n because it's a linear search. Okay, I might get really lucky and it takes theta 1, but I'm doing a worst case analysis here. So, and often what I really care about is the worst case because, I want to know how bad could this thing be. So this is a linear search that also takes theta n. So I've got a thing that takes theta n, a thing that takes theta n, and a thing that takes theta n. So remember with complexity analysis, we did this in the hierarchical decomposition part of the complexity analysis section. We have to multiply the inside of a loop by the amount of times the loop runs. So that means this thing takes n. I multiply it by n, I get n squared. I multiply by n again, and I get n cubed. Okay, so that means this thing takes theta n cubed in the worst case. That kind of sucks, right? That's a pretty awful complexity. And the worst part about it is that it just checks if a set of marriages is stable. It doesn't even construct a set of stable marriages for us, which is really what we want to do. This just checks, right? It just verifies. Now, the question is, can we do better? And the answer, because it's written on the slides, is we can do better. Now, if we know we can do better, let's look at this, right? We said for every woman W. Now, there's nothing we can do to make that not take n, right? It has to loop over every woman. So there's nothing we can do to that part of the algorithm to make it take less time than N. Okay, then we say for every man B that W likes more than her husband M. Now what we said is that it's possible that she likes every other man more than her husband. And in that case, we have to loop over every other man. There's nothing we can do about it. So it's going to take theta N. So these two components of the cost, we can't do anything about, right? But this one, if B likes W more than his wife, we found whether B likes W more than his wife by doing a linear search. Okay, but that was a choice. That was something we didn't, we can design how we code this if B likes W more than his wife. And if we code it as a standard linear search, it's going to take us theta N. But can we do better? Well, I just want to know if man naught, for instance, likes woman 1 more than he likes woman 3, right? And I had to do a linear search to find out. But what if I instead stored the rankings of the women, so that now I could just look up the ranking instead of having to linear search for it? If you didn't fully understand that, don't worry, I'm going to go into a lot more detail about that. So what we can do is we can convert this preference array into a ranking array. Okay, now a ranking array is the same information but organized differently. So if we look at the preference array, the axes are the man and the rank, and the item in the array is the woman, right? So I'm saying man naught ranks woman naught, so the woman is the number on the inside, ranked 0, right? So the rank is on the axis. And what that means is that it's really efficient if I want to look up man naught's favorite girl or something, or man naught's least favorite girl or woman, because I can just go index naught on the y-axis, index naught on the x-axis, and look it up. But that's not what I care about. What I care about is comparing the man's ranking of 2 women. So I instead construct an equivalent array where the axes are the man and the woman, and the item is the rank. Okay, so I've sort of rotated it in 3D, if that makes sense. So how I can fill in this data, because remember, it's the same data as this array. We said it's just organized differently. So let's say I have man naught, woman naught. What's the ranking? 0. So I can fill in a 0 over here. Okay. Similarly, if I say man naught, woman 1, right? So naught 1. And I want to fill in a ranking here. I go man naught, woman 1, what's the ranking? 2. So I fill in 2. Okay. Man naught, woman 2. Man naught, woman 2. What's the ranking? 1. Okay. Man naught, woman 3. What's the ranking? 3. Okay, so that happens to look the same as that, but that's just coincidence, right? Let's do the next one. Man 1, where does he rank woman naught? So man 1, woman naught, the rank is 1. So I put a 1 there. Man 1, woman 1 is the next thing I want to fill in. So man 1, woman 1 has a rank of 2. So I put a 2 there. Then I've got man 1, woman 2 to do next. So man 1, woman 2 has a rank of 0. So fill in 0. Man 1, woman 3. So man 1, woman 3 has a rank of 3. So I put it in there. So you'll see this one has changed, but the actual meaning of the numbers hasn't changed. I've just sort of, like I said, I've kind of rotated it in 3 dimensions, where this was man, rank, and woman, and now it's man, woman, and rank, right? So I'll just fill in the rest here. In fact, it may be worth, as an exercise, seeing if you can fill this in correctly. And then the next slide will show you whether you have. Okay, so now for men, instead of having a preference array, I'm going to keep this ranking array. Okay, so I've replaced it over here, and now I have a ranking array. Now, the question is, how does that affect the complexity? Now we say, well, for every woman W, so that thing still takes theta N, right? Nothing we can do there. For every man B that W likes more than her husband, remember we said that could be every man. So in the worst case, it's still theta N. There's nothing we can do there. But if B likes W more than his wife, let's look at how we would do that. Okay, so let's take the same example of woman naught being married to man naught. All right. Now we want to know if she would run away with man 3. So man 3, we want to know, would he run away with woman naught? So we say, well, look, he's currently married to woman 1, and he's ranking for woman 1, so that's 3, 1, right? Man 3, woman 1. So man 3, woman 1 has a rank of 0. Okay. And we want to know if he'd run away with woman 0. So man 3, woman 0 has a rank of 1. So that clearly he prefers woman 1 because the rank is 0, right? So that means that the lower number means that she's higher up in his preference list, right? So he prefers woman 0. Okay, does that make sense? The only really tricky part to think about there is that lower numbers means he prefers that person, because lower means sort of earlier in his preference list, right? But the cool thing was that now if I wanted to check which woman he preferred, I just did 2 lookups. So it was constant time. If I wanted to know whether man 3 prefers woman 2 or woman 3, I could go and look, well, woman 2, he ranks 3, and woman 3, he ranks 2, so he prefers woman 3. But that was constant time. I just did 2 lookups. Okay, so constant time means I get a theta 1 there. So the total complexity is now theta n squared. And the difference between n squared and n cubed is huge, right? So, or I could say the ratio is huge, but then that would mean, well, it's n. But basically n cubed is garbage and n squared is, well, slightly garbage, but slightly less garbage than n cubed is. Okay, but what this introduced, and I think this is a very important thing, is the concept of how important your data structures are. Now I know you'll have seen some of that with Richard before, and earlier on in the course, but here all we did was change the data structure. We didn't change the algorithm at all, and we went from theta n cubed to theta n squared. This text of the algorithm didn't change at all, right? But because we used the data structure that was better suited to the algorithm, we brought down the complexity dramatically, right? And this idea will be sort of fundamental in your understanding of computer science as you go forward, is that data structures are just a huge part of how well an algorithm performs, right? So we often think the algorithm is the central thing. If we have a better algorithm, we'll do better. I mean, yeah, that's sort of axiomatically true, but it's also true that a better data structure will always do better. Okay, so that brings us to the end of this lecture. And I think hopefully this gave you some idea of where we're going with the stable marriage problem. In the next lecture, we'll look at a solution to the stable marriage problem, and we'll look at its complexity and how we prove whether it's correct. Okay, thank you, everybody.